All right, hello. We're back for the Sunday slash Monday edition of Math 341. I guess this is our second to last week of instruction and new material. Trying to think if there are any major announcements. No major announcements. Of course, assignment 9 went up there on Friday, so that's ready to go if you would like to proceed. Yeah, so let's get straight to it. Oh, happy Easter. Right. I hope the bunny was good to you. Wasn't especially good to me, but that's all right. It was good to the kids. Okay, so last time, let's recall, we were talking about continuous functions, so we had f with the following theorem. Let me just recall this theorem. So if f is a function whose domain is a closed bounded interval a comma b into the reals, and if it is continuous on all of AB, then f is bounded on AB. And we might as well even recall what that means, i.e., there exists some, say, capital M greater than 0, such that the absolute value of f of x is less than or equal to m for all x in the domain a comma b of f. Okay? So being bounded on a given domain means that that the absolute value of the function does not exceed a certain fixed quantity, in this case capital M. And what this theorem is saying is that if f has for a domain a closed bounded interval and is moreover a continuous function on that closed bounded interval, then it is automatically a bounded function on that closed and bounded interval. And we are going to use that fact to prove the so-called max-min theorem. So I asked my kids to unload the dishwasher, forgetting, of course, that they cannot do anything together without it devolving to some kind of argument about who's doing more and what. But hopefully the racket will die down. Okay, so we're going to use this boundedness theorem to talk about the max and min of a function. So let's start with a definition. So you have a function just from some domain A into the real numbers R. We say that f has an absolute max at some point, I'll call it x upper star, in A, if f at x upper star is greater than or equal to f of x for all x in the domain of A. Okay, so at this magic point x star in the domain, the value of the function f is greater than or equal to every other possible value of the function on the entire domain of A. Now, notice I said it has an absolute max, not the absolute max. That's because this phenomenon could occur at many points in the domain. So any periodic function, like if you take a sine wave or something, of course that has an absolute maximum at 1, if you look over the whole, say, real line. But that absolute maximum occurs over and over again, right? So that's just an absolute maximum. Similarly, f has an absolute min at some other point, call it x lower star, belonging to A, if f evaluated at x lower star is less than or equal to f of x for all x belonging to A. Okay? So it's a point at which the value of the function is smaller than or equal to every other possible function value. All right, so those should be familiar concepts to you from first year calculus, say. Okay, and also the next theorem coming up here should be familiar to you. What will be different is that we are actually going to prove this theorem. Okay, so here is the theorem. The max, min, value theorem. Okay, and what it says is that if f from a closed bounded interval a comma b to R is continuous on that entire closed bounded interval, then there exists x upper star and x lower star belonging to that interval such that f upper star, or f of x upper star, is an absolute max and f lower star is an absolute min. Okay. Another way to say that is that if f is a continuous function on a closed and bounded interval, then somewhere on that interval f will actually achieve a maximum value and it will actually achieve a minimum value. Okay? Oh right, and a few examples here I wanted to mention. Just keep them out. Right, so I would like to give some examples that illustrate why all of the assumptions in this theorem are crucial. Okay, because anytime you prove a theorem, you don't want to make any assumptions that aren't necessary, because then, of course, you could get rid of those unnecessary assumptions and have a better theorem. So, let's see those examples. All right, so let's note the interval must be bounded. Okay. Since, okay, you could take the function f of x equal to x and see that that has no max on the interval from, say, 0 to infinity. Okay? So this set here, this domain, it's an interval, for sure. It's even a closed interval, because if you take any sequence in here, which is Cauchy, the point it converges to will be contained, again, in this interval. However, it is not a bounded interval, right? And then, of course, you can see that this function, f of x equals x, will not have a maximum value on this set here, because no matter how big a value I give you, you can always find me a bigger value of x, such that the value of the function, being then equal to x, is also bigger than the value I gave you in the first place. Okay, so the interval has to be bounded. The interval must be closed or we could have f of x, say, is equal to 1 over x on the domain 0, 1. Okay? And as we all well know, as x approaches 0 from the right in this case, the function f of x just gets arbitrarily large. It blows up, it goes to infinity, and so there's no maximum value for this function on this interval. Now here the interval is bounded, and the function is continuous. What fails is that the interval is not closed. Okay, so in each one of these three examples, I'm taking away only one of the three assumptions and demonstrating that no matter which one of the three you take away, you're going to run into trouble. Okay. And then we'll have one more example here. Which of course shows that it has to be continuous. So f must be continuous, or we say could have f of x be equal to 0 when x is equal to 0, and 1 over x if x, say, belongs to the half-open interval from 0 to 1, right? So then the domain of this piecewise defined function here is, in fact, the whole closed bounded interval from 0 to 1. However, the function is not bounded on that domain, since, of course, x could get very close to 0, and this would get very large. But it is nevertheless defined on that domain. The thing that fails is continuity, of course. F is not continuous at x equals 0. Okay? So there you have it. 3 examples showing that each one of those 3 assumptions in the original theorem is necessary. Okay? Now we would like to prove the theorem. So we would like to prove that the max and min are achieved. Okay, so proof of the theorem. So what I'll do is I will only prove that the maximum is achieved. Okay, so I'll find this point x upper star where the max is achieved, and the argument for f of x lower star where the min is achieved is similar. Okay, so we will only find x upper star in the interval AB such that f at x upper star is greater or equal to f of x for all x in AB. In other words, an absolute maximum for the function f occurs at the point x upper star in AB. Okay? So, we have that f is a function from AB to R, and that it is continuous. Hence, the image f applied to the entire domain AB is bounded. So, this is a bounded set, right? And it's also not empty. And any bounded non-empty set has both a supremum and an infimum, but for now we'll be interested in the supremum. So we will let, say, capital M be equal to the sup of the set F applied to AB. Okay, so that is the supremum of all the possible values of the function f on AB. Okay? And the idea is going to be that we're going to find, for every epsilon greater than 0, or rather for every n in the natural numbers, we're going to find some point in this interval from A to B such that f of that point is, well, of course, necessarily less than or equal to m, but on the other hand, thanks to the properties of the supremum, is going to be strictly bigger than m minus 1 over n. And then from that sequence of points, we're going to find a convergent subsequence, and that's going to give us our x upper star. Okay? So, let's see how that works. So, we can thus find for every natural number n some x sub n in the interval from A to B such that value of the function at xn, f at xn, is going to be strictly bigger than the sup of all the function values minus this small positive number 1 over n, and then, of course, necessarily less than or equal to m itself. Okay. So you can always find, given any natural number n, you can always find some point xn, maybe more than one point xn, but at least one point xn in the domain, right, such that f at that point xn is necessarily less than or equal to the sup, but also strictly bigger than m minus 1 over n. In other words, it's getting very, very close to the supremum itself. In a perfect world, these xn's would converge. And then, by the miracle of continuity, we could say that, well, the xn's are converging. And then the function, f of xn, that will also have to converge to some number. And because that number will be sandwiched in between these two guys, the Squeeze Theorem will tell us that whatever that limit is, it has to be m itself. However, of course, xn is not necessarily a convergent sequence. But we do know that every one of those xn's lies in the interval, the closed bounded interval from a to b. In other words, xn is greater than or equal to a, and xn is less than or equal to b, right? And that tells you that xn is a bounded sequence, right? And by Bolzano-Weierstrass, every bounded sequence has a convergent subsequence. So there exists some x and k converging to a point, I'll call it x upper star. And again, because our domain is a closed and bounded interval, the limit of this subsequence, which now exists and is equal to x upper star, that has to be less than or equal to b and greater than or equal to a. In other words, it belongs, I shouldn't say that. Belongs to a. It belongs to this interval, a comma b. Okay. Right. Yeah. It's been a long day. The Easter Bunny has to get up early, to make sure all the treats are laid out. Carefully hidden so that not only will they find a bunch today, but they'll keep on finding them all week long. And the Easter Bunny is therefore absolutely exhausted. But we will soldier on. Okay, so now we've got a convergent sequence, a convergent subsequence to some point in the interval. So by continuity, f of x and k has to converge to f of x upper star. Okay? So that much we get for free from continuity. And from the discussion earlier, if you look at f of x and k, it has to be less equal to m, but it's also going to be greater than m minus 1 over nk, which tells you, right, if you think of this number here as the constant sequence m, and this as a sequence depending on k, then what you've got here is an instance of the Squeeze Theorem, right? Because you've got this guy, these f of x and k's, they're sandwiched in between the constant sequence m and this other sequence, m minus 1 over nk, and that sequence over there, this guy is converging to m. This guy is certainly converging to m, and this guy converges, and moreover, by the Squeeze theorem, then has to converge to m. So f at x and k also converges to m. Okay? So we've got that f at x and k converges to f at x upper star by continuity. We've also got that f at x and k converges to m, the supremum of the function values, using the Squeeze theorem. And a convergent sequence can have at most one limit. Okay, so the limit, if it exists, is unique, meaning that m has to be equal to f at x upper star. In other words, the value of the function f at x upper star is exactly the supremum of all the possible function values, and that is your absolute maximum. Okay? So that concludes the proof right there. All right. So so the idea of this section 5.3, is that we're looking for consequences of continuity when the domain of the function is a closed bounded interval. And it turns out there are lots of pleasant consequences of continuity in that case. So the next theorem is again a theorem that you see and that you learn in first year calculus, but that you, of course, do not prove in first year calculus, but which we will prove now. So I think in the textbook they call this location of roots theorem. It's basically, as we shall see, this is the guts of the so-called intermediate value theorem from first year calculus, right? So remember, the intermediate value theorem says that if you have some, I'll just briefly sketch it. Right? So, well, let's start here. The location of roots theorem is going to say that if you have some closed bounded interval, AB, and if you have a continuous function on that interval with the property that at one endpoint the function is, say, negative, and the other endpoint it's positive, or possibly at one endpoint it's positive, and at the other point it's negative, all that needs to be true is that the sign of the function at opposite ends of the interval needs to be opposite. You know, one's bigger than 0, the other's less than 0, etc. Okay? And the point is that if you have that situation, if you have either of these two situations, then evidently from the picture, and indeed in theory and practice, that function is going to have to cross the x-axis somewhere along the way. That's what continuity means. You can't take a break. You've got to hit every point on the way. Okay? And so that's what the location of roots theorem is going to say. It's going to say that this point here, we're going to call C along the x-axis, that always exists. There's always a C where the value of the function is equal to 0. Okay? All right, so let's write down a formal statement for this guy. And I have to apologize in advance because this is one of those theorems. I mean, the other one that comes to mind, let me see. The other one that comes to mind is the subdivision proof. So if you recall, we had a couple of proofs that every bounded sequence has a convergent subsequence. One of those proofs involved basically repeatedly subdividing a given interval and seeing that the interval you chose, the next smallest interval, still had infinitely many points from your sequence in it. But it was a kind of algorithmic, repetitive piece of code, if you like, that generated a whole sequence of smaller and smaller intervals. And it was kind of a lot to write down at once, okay? And it was very, very helpful to have a large chalkboard where I could leave the entire argument up on the chalkboard and sort of cycle through it 2 or 3 times with you and try to make sure that you understood what was happening, the sequence of things here. The proof of this theorem is, regrettably, to a degree, given our circumstances, similar, okay? It requires kind of a turning of the crank on a piece of code, and it's going to be a little bit hard to keep it all sort of in your head, so I would recommend, at this point in the lecture, if you've got another device with you, of course you have another device with you, you always do, I would recommend having a look at the notes for today to follow along in there, just to help situate whatever's on the board at any given moment. Oh, I'm going to sneeze. Oh, I had terrible allergies. Indiana is the worst. I like the winter when everything is nice and dead. Just dead. Pave the world. Anyway. Okay. Location of roots theorem. So let's let f from a closed bounded interval a, b to the real numbers r be continuous. And suppose that either f of a is less than 0 is less than f of b, or you've got the opposite situation, say f of a is greater than 0 is greater than f of b. It follows that f of c is actually equal to 0 for some c belonging to the open interval from a to b. In other words, if the function is above the x-axis at one endpoint and below it at the other endpoint, it's got to cross the axis somewhere. Similarly, if the roles are reversed, the function's below the x-axis at one endpoint and above it at the other endpoint, again, it's got to cross the x-axis on the way. All right, so that's the location of roots theorem. Any questions? No questions? Great. All right, so let's try and prove this. So I think before I start just writing down sort of like detailed, airtight argument, I want to give you the idea of how it goes, okay? So let me even make that a little bigger. Let's make that bigger. All right, so let's assume here that this is our function, f of x, and here, of course, is the point b, comma, f of b, and here is the point a, comma, f of a. So I am taking the specific situation where f of a is less than 0 is less than f of b. Okay? Right. The argument will be completely analogous for the case where f of a is greater than 0 is greater than f of b. We're just going to go through the details for this case. Okay? So here goes. And maybe I even want to adjust this a little bit because let me make this function a little less symmetric. Okay? So eventually, somehow, we want to locate this point C, right? Because that is the point at which the value of the function is equal to 0. Right? That's what we want to show exists. So what we're going to do is at the first stage, we're going to look at the point P, I'm going to call it P1, and that's going to be the midpoint, a plus b over 2. Okay, so again, shades of the Bolzano-Weierstrass theorem proof, right? We're going to take this interval and we're going to cut it in two. And again, just like in the proof of the Bolzano-Weierstrass theorem, we're going to want to choose one half or the other of this interval to be the next interval in our sequence. And we're going to build a whole sequence of intervals, and they're going to get smaller and smaller and smaller and smaller in such a way that eventually you will wind up with a nested sequence of intervals getting smaller and smaller such that their intersection is in fact just a point. Okay, and it's that point, it turns out, that will be this point C here. Okay, so the question then is, now, having put this midpoint in here, I've cut my interval into two pieces, right? And I would like to decide which of these, so I'm going to say that interval number 1, I'm going to make a whole list of intervals, but interval number 1 with endpoints A1, B1, well, that's just going to be the original interval, the domain AB. Okay? And then I'm going to want interval number 2 to be one half or the other here, so I'll call the endpoints A2 and B2. And so which half do I want? Well, I'm going to want to pick the half where the function still crosses the x-axis, okay? Right? So either the value of the function f at this midpoint P1 is less than 0, which is the case here, in which case you cannot be sure whether or not the function f crossed the x-axis somewhere between here and here. I mean, it's entirely possible, but it's not guaranteed, okay? And we want guaranteed. However, if you look at the other half here, then the value of the function at this endpoint is, of course, less than 0, and the value of the function at the other endpoint is greater than 0, okay? That's the interval we're going to pick for our A2, B2. So in this case, it's going to be A plus B over 2, comma, B. Okay? And then what's going to happen is we're going to, now this is our new interval. This is the chosen one, if you like. Okay? This is the chosen interval. And what we're going to do is repeat the process. Again, similar to the Bolzano-Weierstrass proof, we're going to iterate this process, and what's going to happen is that we're going to find the midpoint of this new interval. We'll call that P2, say. All right, and once again, we're going to want to choose one half or the other. And once again, the criterion for which half we choose is going to be on which half here can we guarantee that the function actually must have crossed the x-axis, okay? And since it does, in fact, cross the x-axis somewhere in the big interval, it's going to have to cross the x-axis somewhere in between. Now, there's a slight wrinkle here that I kind of glossed over in the first step, which is that you could get extremely lucky. Okay, you could get extremely lucky in that when you first pick this midpoint, P1, halfway between A and B, it's possible, unlikely but possible, that f of that midpoint is already equal to 0. Okay, so if that is the case, right, so if f at the midpoint is actually equal to 0, you stop there. That's it. You're done. You found your C. Whatever that midpoint is, call that C. You're finished. Okay? So you only have to continue this subdividing and choosing of one half or the other procedure if you didn't automatically somehow land on a function value of 0 right there at the midpoint. This is exactly why I kind of scribbled out the original function I had and put this little wobble in my function, just to avoid the appearance that that somehow you just got lucky and then you could quit as soon as you found that the function was equal to 0 at the midpoint. The same thing happens at the next stage, right? So now I've got this smaller interval. This is the chosen one. This is I2, okay? And I want to repeat the process. So I find the midpoint, P2, okay? So P2 is going to be A2 plus B2 over 2. And once again, I'm going to have to check if I get lucky. I might get lucky. It might be the case that f at this point on the x-axis is actually equal to 0, okay? In which case, once again, if you're lucky enough that f is equal to 0 at that midpoint, fine. Then call that point C. Now f of C is 0, and you're done. But if not, then the value of the function at this midpoint is either above 0, as it is in this example, or possibly in another example below 0. But it's not equal to 0. And what that means is that one half or the other of these two is going to have the property that on that half, the function actually crosses the x-axis. And that's this half in here. Okay? And so, having found I2, which is from here to here, I subdivide it into two pieces, and then I pick the one where the function is still crossing the x-axis, and that is going to be my I3. Okay? And I keep going. All right? So I'm going to just turn the crank on this over and over and over again. And what I'm going to get so again, we're kind of just doing a heuristic version of this proof before we do the detailed version, if you like, before we dot all the I's and cross all the T's. Okay, so we are going to get a sequence I sub k. Each I sub k is going to be a closed bounded interval such that and again, similar to the Bolzano-Weierstrass theorem, at each stage, okay, this I sub k is going to satisfy a few properties. And the idea is that once you have I1, I2, I3 up through I sub k that satisfy these three properties, you can always turn the crank and find I sub k plus 1 that has these three properties. Okay? Such that 1, I guess I1 contains I2. So they are nested. That's property number 1. Property number 2 is that for each of them, f at the, I guess, left-hand endpoint, f at a sub k is less than 0, is strictly less than f at b sub k. Okay? And finally, the lengths of these guys, the lengths of these intervals are rapidly shrinking. So the way to quantify that would be to say that if you look at the length of the kth interval, which would be given by the difference between the endpoints, b sub k minus a sub k, then that is going to be 1 over 2 to the k minus 1 times the width of the original interval b1 minus a1. Okay? So that little iterative procedure that I was showing you in the diagram, okay, is meant to produce a sequence of closed bounded intervals a sub k, b sub k, which have these three properties. Okay? And the little wrinkle is that at every stage, if you assume you have I sub 1 through I sub k, and they satisfy all these nice properties, then you're going to try to figure out what I sub k plus 1 should be. So you're going to take I sub k, you're going to chop it in 2, okay? You're going to find the midpoint of I sub k, and before you go on to find I sub k plus 1, satisfying these three lovely properties, you have to check, is it already perhaps that we've hit the lottery? Is it already perhaps the case that the midpoint of I sub k is in fact a point where the original function f is equal to 0? If that's the case, then that midpoint of I sub k, that's your c. Okay, that's where the function is equal to 0, and you stop. You only keep going. So producing an infinite sequence of intervals with these three nice properties depends on you basically losing the lottery every single time, which if you played the lottery, you'll realize is really easy to do. Okay, so in all likelihood, with probability approaching 100%, you will fail every time to have the midpoint be the magic spot where the function is equal to 0, and instead you will keep on going and you will wind up with an infinite sequence of nested closed bounded intervals like this, which have the property that at the left-hand endpoint is less than 0, the right-hand endpoint is greater than 0, and have the further property that the widths of these intervals is going to 0, okay? And then what's going to happen is that the intersection of all of these intervals here, okay, that's not just going to be non-empty, which is the basic thing guaranteed by the nested intervals property. It's also, because of property number 3, in fact just going to contain a single point. And that single point is going to be simultaneously the supremum of these a sub k's and the infimum of these b sub k's, meaning that both that the a sub k's form an increasing convergent sequence, the b sub k's form a decreasing convergent sequence, and both of those sequences converge to the same point, namely the point, the unique point, which is in the intersection of all of these intervals. That point, that point is the magic point C, where the function is equal to 0, okay? And the way in which we will see that is that, well, f is continuous. So I've got these a sub k is converging to c, b sub k is converging to c. So f of a sub k has to converge to f of c, and f of b sub k has to converge to f of c. But because of these two inequalities, you know the limit of the f of a sub k's has to be less than or equal to 0, and the limit of the f of b sub k's has to be greater than or equal to 0. And the only way that that limit can be both greater than or equal to 0 and less than or equal to 0 is to be equal to 0 itself. Thus, f of c is equal to 0. Okay, so that is the heuristic explanation. And I think, in fact, that was a good way to go. And then next time around, I will try to give the detailed, gory explanation and write down the bit of code that you need to iterate. And that will prove the theorem. All right, stay safe, wash your hands.